Hello everyone, and welcome to AISC's live webinar, Design for Stability, using the 2010 AISC Specification. Today's webinar is being presented by Louis F. Geschwinder. My name is Brent Liu, and I'm with AISC's Continuing Education Group. All right, with that, I want to introduce today's speaker, Louis F. Geschwinder, PE and PhD. He is the former Vice President of Engineering and Research at AISC, and Professor Emeritus of Architectural Engineering at Penn State University, where he taught for more than 40 years.
Thank you very much, Brent. Let me say good morning to half of you and good afternoon to the other half. I'll try to make this seminar meaningful. And as Brent has said, if you have questions, type them in. If we can answer them over the webinar, we will, but if we can't, we will certainly try to get back to you with answers. I've shown the outline here. We're going to start by talking about design for combined forces because that's really where all of these issues of stability show up. Then we'll talk about the stability analysis and design requirements, the basic requirements, and then how we determine the required strength. There are three methods in the specification for determining the required strength, and we'll cover all three of those, if not completely, at least briefly. And then we'll look at a summary of the methods and a couple of simplified approaches that we're able to use. So Chapter H is the chapter of the specification that addresses design for combined forces, and it's where this information has been found in the specifications for quite a few years. Section 1 is doubly and singly symmetric members subject to flexure and axial force. And that's what we're going to be looking at today. So the interaction equations in the 2010 specification are the same as what they were in the 2005 specification, and very, very similar to what they were in all three of the LRFD specifications, but a little different from what you would have seen in the old ASD specifications. So let me just look at them quickly here. You note that they are given in terms of force and moment rather than stress, and it is the required over the available, and that's the standard format of an interaction equation. So if you look at slides 10 and 11 in your handout, you'll see the definitions of these things. Let me just stay at this slide and point out that PR is the required axial strength, and it's either LRFD or ASD, and P sub C is the available axial strength, and again, either ASD or LRFD. M sub Rx and M sub Ry are the required moment strengths, and M sub Cx and M sub Cy are the available moment strengths. Now the PR and the MR are second-order strengths. That's what we'll be looking for, and that's why we need to deal with the stability design requirements. And so this slide shows a plot in two dimensions, in other words, just one axis of bending, of those two interaction equations. Now if you're checking a column, a beam column, you've got the typical available tables in the 14th edition manual, the axial compression table, table 4.1 for W shapes, and then for beams, you have the ZX table, table 3.2, and you have the beam curves that take into account unbraced length, that's table 3.10. And if you're looking for y-axis bending, you have the ZY tables, table 3.4. This is what we have had for years and years, but something that's relatively new are the combined force tables that are available in Part 6 of the manual. And I would encourage you, if you haven't looked at these before, to take a good look at these tables because it provides answers to all of the questions. What's the available axial strength, bending strength about the x-axis, bending strength about the y-axis, and even tensile strength, all in one location for a particular cross-section. So what we see on the left axis is the effective length, KL, with respect to the least radius of gyration, RY. And so you would use that part of the table to obtain information for the column, for pure compression. And you use the table just like you use the pure column tables. The next part of that definition says, or the unbraced length L sub B in feet for XX axis bending. Now the values in Table 6.1 are the first time we have actual tabulated values for lateral torsional buckling. In the past, you just had the beam curves, but now you can go into this table with an unbraced length and have a table value. Then down at the bottom of the table, we have the values for y-axis bending and tension yield and tension rupture. So take a look at those and become familiar with them, and I think you will find them to be quite useful. Now the basic design requirements are covered in Part B of the specification, and B3.1 is where it provides guidance on determining the required strength. It says the required strength of structural members and connections shall be determined by structural analysis for the appropriate load combinations as stipulated in Section B2. Now that's where you get your ASD and LRFD load combinations. It then says design by elastic, inelastic, or plastic analysis is permitted. So normally we're dealing with an elastic analysis, but there are opportunities to do other kinds of analyses. Then B3.5 is designed for stability. And it says stability of the structure and its elements shall be determined in accordance with Chapter C. So what does Chapter C say? Chapter C says it has general stability requirements in C1. In C2, it tells us how to determine the required strength. And in C3, it tells us how to determine the available strength. And the key here is that the approach you take for determining the required strength is going to dictate the approach you can take for determining the available strength. Those are the things that we want to look at. So under general stability requirements, no matter how you're going to end up analyzing your structure, stability must be provided for the structure as a whole and for each of its elements. The effects of all of the following, and we'll see the list in a moment, all of the following on stability of the structure and its elements shall be considered. Now I highlighted in red the word considered. That is an extremely important part of the provisions because we give a list here of 5 things that must be considered, but that does not mean that you have to include all of those things all the time. This is where your engineering judgment has to come to bear. So number 1, flexural, shear, and axial member deformations must be considered, and all other deformations that contribute to the displacement of the structure. Seems like a rather logical thing. Number 2, second order effects, both P delta, P big delta, and P little delta. The sway and the member effects must be considered. Number 3, geometric imperfections. Number 4, stiffness reduction due to residual stresses. Says here due to inelasticity, and they come from residual stresses primarily. And 5, uncertainty in stiffness and strength. And then there's a concluding sentence, all load-dependent effects shall be calculated at a level of loading corresponding to LRFD load combinations, or 1.6 times the ASD load combinations. Okay, we're going to talk about that 1.6 later, and it's given as a variable alpha, so keep that in mind. But the thing to recognize at this point is that what the specification is requiring is that you do all of these analyses at the ultimate load level. LRFD load combinations are at the ultimate level. The ASD load combinations are not, and so they must be amplified to get them up to the ultimate load level. It goes on to say that any rational method of design for stability that considers all of the listed effects is permitted. So again, an important concept, any rational method. we're going to provide a method, or three methods actually, but if you can come up with another rational method, it is permissible to take that route. So any rational method, this includes the methods identified in section C11 and C12. Well, the method identified in section C1.1 is the direct analysis method. The methods identified in section C1.2 are called the alternative methods of design. And it then references you to Appendix 7, where we have the effective length method and the first order analysis method. Now this organization is a little bit different than the organization that you saw in the 2005 specifications, but the provisions are essentially the same. All right, so let's look at the things we have to consider: flexural, shear, and axial member deformations, and all other deformations that contribute to the displacement of the structure. I've got this simple little structure, 2 stories, 2 bays, fairly large members, and large lateral loads. And what I want you to take a look at are the deflections that we get from the different ways that we can calculate things. So here, if we calculate the lateral deflection at the top of the structure, up there right there at delta, and we include axial, flexural, and shearing deformations, we're going to get a deflection of 2.94 inches. But if we only include flexural and axial, we get 2.42. And if we only include flexural, we get 2.24 inches. So what you see is that by changing what you include in your analysis, you're going to get a different answer. Well, which is the right one? In this particular example, it sure appears that if we want to get a full picture of our analysis, we would want to use flexural, axial, and shearing deformation. But this particular structure was selected in such a way that we would get fairly substantial differences. Other structures, you may not have that same magnitude of difference, and so again, it's up to you to determine what you think you need to do. But if we go one step further and incorporate rigid ends, in other words, we go from the face of the column to the face of the column, and from the face of the beam to the face of the beam, and don't include what's going on within the joint, just use rigid joints, the deflection, the same deflection, is all the way down to 1.79 inches. So we've got to be careful what we include. Now, one of the things that it does not say in the specification is that you have to model the supports correctly. I don't think anybody would question that that's really what we're supposed to do. But if you look at what happens and we model the supports as pins rather than as fixed supports, the deflection now is 7.11 inches. So you see we can go quite a range from 1.79 inches to 7.11 inches depending on how we model the structure. So we've got to consider what we include and include the correct things. Now, second order effects, both P big delta and P little delta. Well, P big delta is the sway. And so you see that if you take a look at that load now moved over that distance, which is delta, there's going to be an additional moment down here, which is whatever that force is times that sway displacement. That's the P big delta effect. And if we go to what's going on along the member, you see you have this little bit of deflection along the length of the member, and the axial force in the member times that deflection, again, gives you other moments to add to what's going on in the member. So if we take this very simple structure and we do a second order analysis, what we find is that we follow the blue line. We follow this line right here and move out. so that at some particular load level, we get an instability. The structure buckles. We need to know that level. We'll talk about that later. But certainly the typical first-order analysis that moves up this line can't reflect the true behavior in the structure. So we need to accommodate a way to calculate the second-order effects. Now, how do we do that? Well, the specification gives us two ways, basically. Either carry out a rigorous second-order analysis. If you do that, then the results of your analysis are the MR and the PR that we were using in the interaction equations. Or you can use an approximate method of second-order analysis, and that approximate method is given in Appendix 8 of the specification. Again, a little change from the 2005 specification, because this material had been in Chapter C. It's now in Appendix 8. And this is what we have historically called the B1, B2 method.
Lou?
Yeah.
Before we move into the B1, B2 method, can you go back to slide 22 for a moment?
Sure. Yes.
The question we have, does the rigid end deflection represent a full moment connection?
No, actually what the rigid end offset represents is what happens in a reinforced concrete structure where very little, if any, deformation takes place within the joint. In steel design and analysis, a rigid connection is what we have when we model the beam from node to node, center line of joint to center line of joint. That would be a rigid connection, but not a rigid end offset. The rigid end offset says, okay, from that point to the face of the column, we have no deformation. But of course we do have deformation in that panel zone. And so the analysis for steel should be going from node to node or center line to center line without using the rigid end offsets. Okay? If that didn't answer your question, type it back in again and we'll see where we go.
Thank you, Lou.
All right, what slide were we at here? Let's
29.
All right. So what we find in Appendix 8 is that if we're going to use the approximate method, the second order moment, M sub r, is equal to B1 times NNT plus B2 times NLT. And the second order force is P sub NT plus B2 times PLT. Now what do these things mean? Well, NT means no translation, and LT means lateral translation. So we have both the force and the moment from those different kinds of analyses. And then we have the B1, B2 amplifiers. B1 takes care of what's called the member effect, which is the P little delta, the bending along the length of the member. And B2 takes into account the sway effect, or the frame effect. We can see in this next slide how we would go about doing our analysis. We first take a little structure that has gravity load and lateral load, and we put on an artificial reaction up here. So here is this thing I've called the artificial restraint force. We put a reaction up there and we analyze that structure, and when we do that, that structure cannot sway sideways. So whatever we get as our forces in the member and our moments in the members, those are the NT, or no translation effect. But that force really isn't there, so we have to analyze the structure when we take that off. And when we take it off, we put that force on in the opposite direction. The structure sways sideways, and those are the results that we call the LT results, or the lateral translation results. Design office practice oftentimes says, well, my structure is sufficiently symmetric, my loading is sufficiently symmetric, that I can take my gravity-only loads, and those will be my no translation loads. And I can take my lateral-only loads, and those will be my lateral translation loads. That works fine. However, in this situation that I've shown, the load is not in the center. And therefore, for gravity load, there will be some sway. And it's up to the designer to determine whether that is sufficient to be of concern, in which case then you would have to go through an analysis that takes out the side sway for the gravity load. So let's look at the B1 multiplier for the member effect. B1 is equal to C sub m over the quantity 1 minus alpha PR over PE1. And if you think about what you use in the interaction equation if you were using the 1989 AISC specification, there was a multiplier in there, C sub m over 1 minus FA over F prime E. This is the same kind of thing. C sub m is a constant that accounts for the moment gradient along the member. All of these amplifications for member effect were developed assuming the moment is constant on the column. For members that are not loaded transversely, but are loaded with moment at one end and a moment at the other, M1 and M2 being the ratio of the smaller moment to the larger moment, and positive if it bends it in reverse curvature, and negative if it bends it in single curvature, you get a reduction factor, C sub m. Now, alpha is 1 for LRFD and 1.6 for ASD, and I mentioned this a little bit earlier, and we're going to still put that off for a while. PE1 is simply the Euler buckling load for a pin-ended column. So K is equal to 1, and PE1 is pi squared EI over K1L squared, which is really 1. Brent, are you hearing those beeps?
No, I'm not.
Okay, I'm getting something, but I won't worry about it.
Apologize.
All right, the B2 multiplier, 1 over 1 minus alpha P story over PE story. PE story is the elastic critical buckling strength in the plane of bending. Okay? It is the strength that the structure has to resist lateral buckling. And P story is the total vertical load supported by all columns in the story. So how do we get that PE story? In the 2005 specification, there were two ways of getting it. One of them used an effective length factor, and the specification committee took that out and left it in the commentary, but took it out of the main body of the specification because it is not an effective way really for determining the buckling load. So we determined PE story, as you see here, based on the lateral stiffness of the structure. So we put some horizontal force H on the story, and we determined the first order drift or translation of the story, delta H. And so PE story, as it turns out, is really a function of the ratio of H to delta H. L is the story height, and R sub m is a factor that accounts for leaning columns or gravity-only columns in the structure. So if all of the columns in your structure are moment frame columns, then the total vertical load on the moment frame columns is the same as the total vertical load on all the columns, and that ratio is 1, and PF over P story. And that means that R sub m is 0.85. If, on the other hand, you have a braced frame in which no load is on moment frame columns, then the ratio PMF over P story is 0, and R sub m can be taken as 1. So you see that R sub m of 0.85 will turn out to be conservative in all cases. Now, how about geometric imperfections? Well, there are two geometric imperfections that we have to account for, out of straightness and out of plumbness. The ASTM-A6 tolerance for out of straightness of a column is the length over 1,000. And this is already incorporated into the strength provisions of the specification and has been. The out-of-plumbness is specified by the Code of Standard Practice. It says the column can be erected out of plumb and amount L over 500. This has not been incorporated in the past. It was brought into the specification with the 2005 specification, and its use is the same in the 2010 specification. So these are the geometric imperfections that we will want to consider. Then the stiffness reduction due to inelasticity. That primary inelasticity comes from the residual stresses in the member and the fact that as you load it, it really does not behave in the typical stress-strain relationship where it remains linear between stress and strain all the way up to yield. But because we are now not talking about just an element, a small specimen, but in fact a whole cross-section, we find that the stress-strain relationship follows a curve similar to what's shown here. And what we should be using is the tangent modulus. The relationship that we have for the tangent modulus can be accommodated through the use of tau sub b. Tau sub b is equal to 1 if the load applied to the structure, 1.0 over the LRFD load or 1.6 times the ASD load, over the yield force in the column is less than a half. But if it's more than a half, then the residual stresses start to have an impact. And that is brought into the specification through the use of tau sub b. And you see it here as the Chapter C of the specification provides for tau sub b. We'll talk more about that later also. Then we get to, yeah.
I'm sorry.
That's all right.
I meant to jump in here sooner. Before we move on, there's a question back on slide 33. Could you clarify, are M1 and M2 due to gravity only?
Yes. Well, if they're due to gravity only, if you've assumed that your no translation load is your gravity only load combination. So the M1 and the M2 are the no translation moments. So if we've assumed that gravity is our no translation, then yes, they are gravity only. Back to 44, right? Right. 44, uncertainty and stiffness and strength, and the uncertainties, the resistance factor in LRFD, the safety factor in ASD, and the tau sub b includes some uncertainties. This is new to the 2010 specification, but it hasn't really required us to do anything new. It's just pointing out that, yes, they are there. So what's really new? What do you as an engineer need to consider that you haven't considered in the past? And you'll note I put on the slide here with 2005 and 2010. If you've been using the 2005 spec, there's really nothing new here. But if you are coming into the unified specification new, first thing, second order effects. Now these are not new. You should have been including them all along, but the concern is that many engineers were not properly including second order effects. So that may be new, depending on where you've been. Initial out of plumbness, that is new with the 2005 specification, so it's the same for 2010. And then residual stresses. The residual stress influence on second order effects. And that's built into your second order analysis. If it's the B1, B2 method or some rigorous method, that's going to be built in there. So there really isn't a whole lot new here that you have to include. What is new is that we have some new ways of actually determining your required strength. We have the direct analysis method in section C2, and the note here says this is the foundation for the other approaches. Then we have the effective length method in Appendix 7.2, and it says essentially what you have been used to. Well, if it's what you're used to doing, how can this new method, the direct analysis method, be the foundation? What that really means is that the limits on the applicability of the effective length method are set based on the direct analysis method. And what you will find if you go back and check the structures that you have designed, I would expect that most of your structures will meet the requirements to be done by the effective length method, which means the way you've been doing it in the past. And then we have the first order analysis method, and this is a new method with the 2005 specification, and it is really the simplest if it's applicable to the structure that you're working with. So the features of these methods, the key for the direct analysis method is that it eliminates the need to determine an effective length factor. Now, if we were talking about the full day seminar on stability analysis and design, we would spend a good bit of time showing why it's important to eliminate the effective length factor because of all the uncertainties in how to actually get a correct value. So it's really a big step forward to be able to do an analysis and not have to use the effective length factor in the design of your compression members. The other feature is the use of notional loads. Now, notional loads are a way to account for out-of-plumbness. You can use these in all three of the methods. You don't have to use them in the direct analysis method. You can actually build your model out of plumb. We'll see that in a minute. But in the effective length method, you must use the notional loads. And then the notional loads can also be used to account for second order effects. And that's what is done in the first order analysis method. So these are the new things, notional loads and eliminating the need to calculate K if you go with the direct analysis method. So remember, C1 talked about all the basic stability design requirements. C2 says, how do you calculate the required strength? For the direct analysis method of design, the required strengths of components of the structure shall be determined from an analysis conforming to section C2.1, which we'll talk about. The analysis shall include consideration of initial imperfections in accordance with section C2.2 and adjustments to stiffness in accordance with section C2.3. It's applicable. The direct analysis method is applicable to all structures. Doesn't distinguish between brace frames and moment frames and shear walls. You can use the direct analysis method for arches. Any structure you can come up with, you can use the direct analysis method. The bottom line, as I've said before, is that K is equal to 1. So in section C2.1, first it says consider all deformations. Well, that's what we've already talked about. That's in the general requirements. Then it says consider second order analysis. And again, that's what we've already talked about in the general part. But it goes on now to say you can use any method as long as it considers P big delta and P little delta. And it gives you an option to ignore the effect of P little delta on P big delta. It says any method. It identifies rigorous methods and it identifies the amplified first order analysis method of Appendix 8 that we've already talked about. C2.1.3 then says include all gravity and other loads. I'm not sure why we put that in the spec. That seems rather obvious to me. And then Section 4 says carry out analysis for LRFD or 1.6 times the ASD load combinations. Well, it's about time we quit putting off that 1.6 discussion and take a look at it here. This is that same little structure that I showed you the second order analysis for earlier, and it follows the curve, and this curve right here is the second order analysis curve. Now, if we assume we have a live to dead load ratio of 3, the LRFD load could be 100, 150, the ASD load would be 100. There's a 1.5 to 1 relationship. So if we analyze the structure for a load of 100 kips right here, and we do a first order analysis, we're going to get a moment of 60 foot kips. That's that part right there. If we analyze it for 150 foot kips right here, we're going to get a moment of 90 foot kips. That's a first order analysis following that straight line. But if we do a second order analysis at a 100 kip level, we're over here now at a moment of 103, and at the 150 foot kip level, we're over here at a moment of 246 foot kips. So the amplification at the higher level is much, much larger. In order to make sure that we pick up that level of amplification, the specification says that we do our ASD loads at 1.5 times the ASD load combination. And so now we're up here, not 1.5, 1.6 times the ASD load combination. So now we're up here at a load of 160 foot kips. And the second order moment is all the way over here at 298 foot kips. So for ASD, had we not done it at the amplified load level, our amplifier would be 1.72, whereas LRFD would be 2.73. And with the amplification of alpha in ASD, it's going to be 3.1. Now this little structure is a very specific structure that has large second order effects, and so the difference you see is fairly substantial here. It's not always that substantially different between the 1.6 ASD and the LRFD. So that's where the alpha of 1.6 comes from. Now how about the initial imperfections? For the direct analysis method, you can either do direct modeling or use notional loads. So here is a model where I've directly modeled the imperfections. The imperfections, remember the out of plumbness was the height over 500. So if I take the height over 500 of a 10-foot story, I get 0.24 inches. And so my first level is out of plumb and amount 0.24 inches. My second level is now moved over an additional 0.24, so it's at 0.48 inches. When I analyze this structure, I get a moment at the support down at the bottom here of 32.4 inch kips and a deflection at the top of 0.105 inches. Keep those numbers in mind, and we'll compare them to what we get when we use notional loads. Now the notional load is 0.002 alpha times y sub I, where y sub I is simply the gravity load at each level, not added up, but at each level. So the load that comes in at this level up here times 0.002 alpha is applied over here, and so on. So for my little structure, if we're doing it in LRFD, alpha is 1, and so my notional load is 0.002 times the sum of 100 plus 100. That gives me a notional load of 0.4 at the top, and down at the lower level, again, it's 100 plus 100 times 0.002, so I get 0.4 again. And if I analyze this structure, I get the same moment at the bottom, 32.4 inch kips, and the same deflection, 0.105 inches. And so either way, you can model the structure out of plumb, or you can use the notional loads in the direct analysis method. Now, it goes on to say, if the second order effects are limited, in other words, if the second order displacement over the first order displacement is less than or equal to 1.7, the notional loads only need to be applied in the gravity-only load combination. So if you think about this, how often is your lateral load resisting system designed for gravity-only load combinations? Not often, right? So this notional load, this out-of-plumbness, it turns out, is rarely going to be an issue for a structure that is designed to resist lateral loads. Now the stiffness adjustment. Two things. To do the direct analysis method, you must reduce all stiffnesses by 0.8. This is the unique part about the direct analysis method. This is something that's not in any of the other methods, and it's because of this 0.8 reduction in the stiffness of the members that we're allowed to have an effective length factor from the design side of 1. There's also the adjustment for TOSA B for the residual stresses, but that you will find in the direct analysis method and the effective length method. So for the direct analysis method, instead of using EI and EA, we're going to use EI star, right, the star representing the modified, and that's 0.8 TOSA B times EI. So it's only the flexural stiffness that's adjusted by the TOSA B, but all of the stiffnesses, shear and axial and flexural, all of the connecting elements, if you model them, everything is adjusted by the 0.8. Now there is another option that if you don't want to use TOSA B in this equation, you can put a notional load on. We're not going to worry about that in this discussion. Following all of those things then, you will determine your required strength. What about determining the available strength? Well, that's really what the majority of the specification is, determining available strength, and that's what you find in chapters D through K. D for tension members, K through HSS connections, the entire body of the specification. The difference is that when you deal with compression members, you're permitted to take the effective length factor K equal to 1. Okay? Now there's also requirements for bracing in Appendix 6 of the specification. But to do your second order analysis of your system, you need to include the bracing in your system. And so there's no need to use any of the bracing requirements in Appendix 6 for column or frame bracing. So the design process is fairly simple. Perform your second order analysis, either B1, B2, or with a rigorous method. Use the nominal geometry, in other words, not the out-of-plumb geometry. Use the reduced stiffnesses, apply your notional loads, and then design the members for K is equal to 1. So let's look at a simple example here.
Lou?
This is a W14 by 99 column. We've done a first order direct analysis. What that means is that we don't need to worry about effective length factor K, but we are going to need to worry about the second order amplification. For this particular structure, a horizontal force of 137 kips on the structure would correspond to a drift of 0.493 inches. Okay? That's a measure of the lateral stiffness of the structure. Now in the given material on slide 66 there, it gave you a moment and an axial force. We're going to assume that the moments come from a lateral analysis, a translation analysis, and we'll assume that the forces come from a no translation analysis. This is just to simplify the rest of this material. So the member amplification, if we do this problem in ASD, we've got C sub m over 1 minus alpha PR over PE1, and we have to remember to use alpha of 1.6. We've got the moments given. Moment at one end was 110 foot kips, and at the other was 161 foot kips. So C sub m is 0.6 minus 0.4 times the ratio of moments, bending it in reverse curvature. So C sub m is very small, 0.327 right here. The Euler buckling strength of the column, notice that I'm using here EI star because this is the direct analysis method. So I've got to use the 0.8 reduction, and I'm not using tau sub b. I'm just using tau sub b equal 1 here because I know that this column is lightly loaded in terms of the yield load. So I get PE1 of 9,600. Taking that information then, because it's ASD, I need to use that 1.6. So I've got C sub m of 0.327 over 1 minus 1.6 times the axial load, 247, over PE1, 9,600. B1 comes out to be 0.341, and it must be 1 or greater because we can't reduce the moment because of second-order effects. And so what we see here is that the reverse curvature of this column means there is no increase required, and B1 is going to be taken equal to 1. For the side sway, or the sway amplification, we have that horizontal force of 137 kips that resulted in a horizontal deflection of 0.493 inches. The entire load on this story is 3,750 kips. And so if we calculated this drift using our reduced stiffness EI, then we can get our PE story. Since it's a moment frame and we don't know anything about being gravity-only columns, we're going to use R sub m of 0.85. So we have 0.85 times the horizontal force of 137 kips times the story height over the delta H of 0.493 inches. We get PE story of 38,300. And so our amplification, 1 over 1 minus, there's the alpha again, 1.6 times the 3750, that's the gravity load on the story, over PE2, or PE story, 38,300. Gives us a B2 of 1.19. So what we have in terms of amplification now is the moment 1.0 for B1, but there was no MNT, plus 1.19 times MLT gives us a moment of 192 foot kips. And as far as the force is concerned, there's never an amplification on the PNT, so that's the 247. And there was no axial load due to lateral loading or lateral translation, so the axial did not increase. So we have to design the column for 192 foot kips instead of this 161 and 247 kips. And using the interaction equation, we find that we need equation H1-1A, and the interaction value comes out to be 0.722. Okay, well less than 1. And of course, we'd have to check it for any other load combinations. If we do that same problem in LRFD, I'm not going to go through all of it. In fact, I'm going to skip ahead. Certainly there are a different load combination, but we have a different horizontal force, 195 kips, and it gives us a different horizontal displacement. We use the same decision in terms of how we divide up our LT and NT information. When we get to our amplification for member effect, you see C sub m is a little different, but it's small. And when we get to PE1, lo and behold, we get the same value that we had in the ASD solution, because the strength, the buckling strength of the column is the same. It's independent of ASD and LRFD. And again, the B1 turns out to be 1. Now when we get to the sway part, of course we have a different P story with different H, different delta H. But when we look at PE story, turns out it's the same as it was for ASD because the ratio, 195 to 0.703, is a constant. It's a measure of the stiffness of the structure. And so our B2 turns out to be 1.16. A little bit different for two reasons. We're not using the 1.6 for alpha, and we have a different relative magnitude of our load. Our amplification factors are a little different, but our strength comes out to be, again, acceptable. But notice that here it's 0.66 for LRFD. So we get different unity check from our interaction equation when we're doing it with ASD or LRFD.
Now, Lou?
Yes?
We do have a couple questions before we move on.
Okay.
First question, when dealing with long, slender columns where KL over R is large, AISC formulas increased alpha up to 1.9. Do we still use this increased alpha with this analysis?
AISC doesn't increase alpha to 1.9. I'm not sure. Let's see. Now, alpha is always 1.6. It's a constant. I'm not sure where Dan's getting that question from, but certainly he can identify that later on, and I'll try to give him an answer for whatever it is he's looking at there.
Okay.
Okay.
Another question: when we calculate drift, do we do that using the ASD load level times 1.6?
Yes. You do it at the LRFD load level. Well, actually, let me back up. It depends on what you're trying to. You can actually just put in an arbitrary load of 1 kip and get whatever the deflection is, because it's the ratio of load to deflection. And that's why I showed in the ASD and the LRFD comparison that PE story comes out the same, because that ratio of load to deflection is the same. Okay? But if you're calculating drift in terms of getting second order forces and moments and all, yes, you do that at the 1.6 times the ASD load combinations.
Okay.
Now I want to look at
one last question, Lou.
Yep.
Sorry. Just one more.
That's all right.
You had talked about stiffness reduction back on slide 62, and the question was, does this apply when using composite sections?
Yes. Yeah, the stiffness reduction applies no matter what your system is. And in fact, if you were combining this somehow with a reinforced concrete wall or something, you'd have to try and figure out how to reduce the stiffness of those other elements. It's not covered in the specification specifically, but anything that is part of your lateral load resisting system, the stiffness has to be reduced.
Okay, thank you.
Oh, okay, let's take a look at these notional loads. I have a very simple little example here. We've got a little structure with a dead load of 75 kips and a live load of 220 kips and a wind load of 20 kips. And for this particular load combination, you see that there is a lateral load of 9 kips. If we determine the notional load, you see it's the sum of the gravity loads, 240 plus 240, gives us the 480 kips. And then it's 0.002 times that. And you'll notice I didn't include the alpha of 1.6, so we'll mention that in a minute. So the notional load turns out to be 0.960 kips compared to the wind load of 9 kips. Okay? Now, if B2 is less than 1.7, we don't even have to worry about the notional load, because it only has to be applied in the gravity-only load combination. So you see these notional loads are very small. Now if we go to the gravity-only load combination, you see now our gravity loads are 295 kips, and our notional load is 1.18 kips. And so our analysis would have to account for that. Even if our B2 is less than 1.7, we still have to have our notional load in the gravity-only load combination. So here it would be 1.18 kips. Now the reason that I didn't use the alpha of 1.6 here is because if we do the B1, B2 method, the alpha is in the B1, B2 calculation, and it doesn't need to be put into the load combinations. Because what happens when we do an analysis with 1.6 times the ASD load combinations, we then divide by 1.6. And of course, if we're not doing a second order analysis, the dividing just cancels out. If we look at LRFD, the only thing that changes are the magnitudes of the forces. And so you can look at those yourself and see exactly the same thing. So in the gravity-only load combination, there is that 1.77 kip notional load. So why use the direct analysis method? Why? We've got this method. When we first started presenting the 2005 specification, we talked about it being the method of the future, the way of the future. Why do you want to do it? Well, you want to eliminate the need to calculate K. And why do we want to eliminate the need to calculate K? Because frankly, we really don't know how to do that correctly. The other reason you want to use the direct analysis method is that you have to. And you have to use the direct analysis method if you have significant second order effects. And you define significant second order effects as either B2 being greater than 1.7 if you're using the reduced stiffnesses of the direct analysis method, or you define B2 as being greater than 1.5 if you're using the normal stiffness. So those are two possibilities, all a function of what you use for the stiffness of your structure. However, if B2 is less than or equal to 1.5, you have three choices. You could use the direct analysis method, as we did, and our B2 was fairly small, or you can use the effective length method, or you can use the first order analysis method. So let's take a look at the effective length method. What do you do with the effective length method? Apply your notional loads in the gravity-only load combinations. You never have to worry about applying your notional loads in the lateral load combinations in the effective length method because you're already working at a B2 that is small enough. You perform your second order analysis, use the nominal geometry, the nominal stiffnesses, and determine K from a side sway buckling analysis. And then there's this little thing here. If B2 is less than or equal to 1.1, you can also use K of 1. How does this differ from the direct analysis method? Well, you don't use the reduced stiffnesses, and you must determine K. That's the only difference. You still have to do second order analysis, either by a rigorous method or by the B1, B2 method, but you still have to do it. So how does this differ from what you should have been doing all along? The only difference is that you need to consider initial out of plumbness. And as with the direct analysis method, it's only in the gravity-only load combinations. So let's talk a little bit about this problem of determining the effective length factor. Most people think of the alignment charts when they think of determining K. But the assumptions that went into the development of the alignment chart are fairly significant when we compare them to what really happens in our structure. First of all, behavior is assumed to be purely elastic, and we know columns are not behaving elastically. We've got these residual stresses in there that tend to have a significant impact on the way columns behave. We assume the rotations at the opposite ends of their beams are equal and producing reverse curvature. Chances are they aren't going to be equal. We assume the stiffness parameter for each column, L times the square root of P over EI, is the same. Again, not likely to happen. And we assume all columns buckle simultaneously. And that is not likely to happen, particularly if we have gravity-only columns working in a system along with moment frames. So what are these gravity-only columns? They're also called at times leaning columns. They are columns that don't contribute to the lateral load resistance of the structure. They, in fact, rely on the lateral load resisting system for their support, but they are extremely easy to design because you design them for K is equal to 1. And here's a little floor plan that shows two moment frames, two perimeter moment frames, one here, in the east-west direction. And then all the remaining columns, the red columns, are all gravity-only columns. So if we simply count columns, 50% of the columns in this structure are gravity-only columns, 50% of the columns are moment frame columns. But if you look at the way the load is distributed, just based on tributary area, 64% of the load on this structure is on gravity-only columns. That number we'll use later on in this example. We'll take a W14 by 120 that's an exterior column, it's part of a moment frame. In this particular load combination, determine the B1 and the B2 and see what happens. So here's the ratio of the moments at one end to the moment at the other, be bending it in reverse curvature, so C sub m is 0.4. PE1, pi squared EI over KL squared. Now we're doing the effective length method, so there is no reduced stiffness in here. So PE1 is 17,550 kips. When we calculate B1, primarily because of this C sub m, because this is bending in reverse curvature, we see B1 is much less than 1, so we will take B1 equal to 1. To determine the sway, instead of calculating the displacement of the structure, I'm going to do it from a design approach and say, well, my lateral load is 150 kips, my service load, and under that service load I'm going to limit my drift to L over 400. What that does is give us a way to get the lateral stiffness term without actually doing a lateral load analysis. Now R sub m, the thing that accounts for the combination of moment frame columns and gravity-only columns, remember we said 36% of the load was on the moment frame columns. So the ratio here is 0.36. That means R sub m is 0.946. And using that in our PE story, there's the 0.946. The H was 150 kips, and delta over L was our drift limit of 400. So PE story comes out to be 56,800 kips. The entire load on the story was 2,270 kips, so our B2 comes out to be 1 over 1 minus 1.6 because we're dealing with ASD times that 2,270 over to 56,800, and we get a B2 of 1.07. So we amplify our moments. B1 was 1, so the no translation moment doesn't get amplified. B2 was 1.07, so the translation moment does get amplified, and we have a required moment now of 165 foot kips. The no translation load was 378. The lateral translation load was 46, which gets amplified by the same 1.07, so that's now at 427 kips. But because we're doing the effective length method, we have to go calculate the effective length. So I simply use the alignment chart, and I assume that everybody remembers how to do that. So we get the G at the top and bottom, assuming the beams are the same at the top and bottom, the columns are the same. We get G of 2.03. We get K in the plane of the frame of 1.6. Out of the plane of the frame, we use K of 1. But now we have to account for the fact that we have all of these gravity-only columns. Now, the best place to find a reference to this particular approach is in the commentary to the second edition of the LRFD specification. And it's a simple approach where you take the nomograph K factor times the square root of 1 plus the gravity-only column load over the restraining column load. Okay? Well, there's the 0.64 times the gravity-only load for the, 0.64 times the total gravity load over 0.36 times the total gravity load. And K has jumped from 1.6 up to 2.67. Using that, we find that KL over Rx over Ry is 20 compared to 12.5 for the y-axis. So from this, we get an axial strength of 782 kips. We check our interaction diagram. We find, again, we're using equation H1-1A. And so with a moment strength of 529 foot kips, the column has an interaction equation value of 0.83, less than 1. So it works. So what we've determined is it works for that loading combination. Now it has to be checked for any other load combination. Now, what do you expect is going to change when we go with LRFD? Certainly the load numbers change. The ratio of moments don't, so C sub m is the same. PE1 stays the same. Important because that reminds us that this is just a measure of the buckling strength or stiffness of that structure. B1, numerically it may be a little different, but it still is going to be 1. When we talk about the B2, again, we've got that same 150 kips. It's a service load, and we're going to limit our deflection to L over 400. So you see neither of these numbers have changed when we go to LRFD. When we go to the R sub m, that doesn't change. That's just a function of how the load is distributed. When we go to the PE story, it has not changed. So again, PE story, PE1, these things do not change for LRFD versus ASD. Our sway amplification will change a little bit because of the magnitude of the load and not using the 1.6. So the difference here is 1.0 times 2445 compared to 1.6 times whatever the other load value was. We amplify our loads, and then we get to the effective length. Well, the effective length calculations don't have anything to do with ASD, LRFD, right? It's the same calculation. So we come back to calculating this K of 2.67. We get our strengths. We get our interaction equation. And, of course, it comes out less than 1. It may be, and it will be, a little bit different than the ASD solution. That value right there will be different, but that's what happens between ASD and LRFD, whether you're talking about combined column, bending and axial, you're talking about pure tension, or anything else. There's going to be a difference between ASD and LRFD, and that's acceptable according to the AISC specification. And just like the ASD solution, we have the other load combinations that we need to work with. Okay, now the other method, the first order analysis method. The first order analysis method has certain limitations. First of all, the structure supports gravity loads primarily through nominally vertical columns, walls, or frames. In other words, it's got to be a fairly regular, simple structure. You're not going to be able to do arches with this or with the effective length method for that matter. Second order effects have to be small. This is the same limit. This limit right here is the same limit that we had for the effective length method. In fact, this number 1 is also the same. And then number 3 here, inelasticity must not be significant. That's really the use of TOS sub B. And although in the effective length method example that I presented, we did not actually use TOS sub B, it could be there if we needed to use it. We can use it in the alignment chart. It's the stiffness reduction factor. In the 2005 specification, it was given as TOS sub A, but it's now TOS sub B. We use the same value for all of these methods. So that limit was not there in the effective length method, but it is there in the first order analysis method. The big difference here is that there is a notional load applied in all load combinations. You only have to do a first order analysis, but you must put on this notional load, 2.1 alpha delta over L y sub I. Y sub I is the gravity load at that level, and that has to be greater than or equal to 0.0042 y sub I. Then you have to apply, when you do the member check, the B1 factor. Now this B1 factor, we saw in the examples that we've done already, is 1 most of the time. If you bend your column in reverse curvature, chances are it's going to be 1. So that won't be a particularly difficult thing to do. But if you go back even further into the old ASD, the 89 ASD, that's the C sub m over 1 minus FA over F prime E. So the process here is just like what you did in the old ASD. Okay, so the available strength now with the first order analysis method, just like before, determine them with chapters D through K, but K is equal to 1. Okay, K is equal to 1. So just like the direct analysis method, with the first order analysis method, you can use K equal to 1. And of course you have to have sufficient bracing stiffness and strength. So perform a first order analysis, use nominal geometry, nominal stiffnesses with the notional load, and then apply the B1 multiplier in checking all of your beam columns. So how does this differ from the direct analysis method? All right? It does not use any reduced stiffnesses. There are notional loads all the time in every load combination, gravity as well as lateral. And there is no need to do any second order analysis except for the B1 calculation. How does it differ from the effective length method then? Well, notional loads are always applied, all right? You don't need to do a second order analysis except for B1. And K is always equal to 1. These are significant advantages if this is the method that your structure meets the requirements for. Now in terms of summarizing all of this, there are a number of places that you can go to get a summary of the methods. Table 2-2 in the manual is one of those places. It shows the direct analysis method, the effective length method, and the first order analysis method. It gives you the limitations and describes the primary differences. Another place to look is on what we call the basic design value cards. Now the basic design value cards came about with the 2005 specification. And there were 2 versions of those cards. And now there is a third version for the 2010 specification. And the version for the 2010 specification, you'll notice in the upper right-hand corner, has a copyright 2011. So this table on the bottom of that basic design value card is essentially the same as the table that you'll see in the manual, table 2-2. Okay, so giving you the same kinds of information. Where do you get the basic design value cards? Well, if you go to any of our seminars, the new spec seminar, you will receive these in that new spec seminar package. They have been available as a download off of the website. They'll probably be available there again. The other thing that's on that basic design value card is a simplified method. Okay? Now this value, or this table here, this one that's on the top of that basic design value card, is also available as table 2-1 in the 14th edition manual. So you can take a look at it there when you get your manual, if you get that before you get any of these basic design value cards. All right? And that method is based on a very simple assumption. As long as B2 is greater than B1, then we can simply multiply all of our moment by B2. That certainly simplifies things because then we don't have to worry about the MNT, MLT. So let's check that example 3 column. We had a load of 424 kips and a moment of 160 foot kips. All right, that's combining the NT and the LT. We had a wind load of 150 kips that gave us a deflection of L over 400. We need to calculate the ratio of the gravity load to the lateral load. So this is the 1.6 for ASD. The 2270 was the gravity load for that problem, and there's that 150. So what we get is this ratio of 24. Our drift limit is L over 400. We can go into this table then, add an H over 400, and look at the values for a load ratio of 20 and 30, and you see that it's 1.1 for either one. Now, we don't recommend that you interpolate, so I would use, if it came out different, just use the larger one. And the reason we don't interpolate is because we're not giving you enough data in here to make it worth interpolating. So what we're going to do then is amplify the load by 1.1, the moment by 1.1. We now have 466 kips and 176 foot kips. With the effective length factors of 1, we get our strengths, and we determine the interaction value of 0.8. Now you will see that that is certainly different than what it was in example 3. But it is a very quick way of getting at the answer. The same thing happens in LRFD. Different numbers for the loads, but not different numbers for the wind load and the wind drift. So now we have different gravity load. So our ratio of gravity to lateral is different. We're now going to go into the table with 16.3 NL over 400. So we're still there at that H over 400, but now we're in here at a ratio of 10 and 20. And like I said, I would not interpolate, so we're going to pick the 1.1, and we amplify our loads, and we do our interaction check. And again, it comes out less than 1. I think if I recall correctly, it was 0.66 before. Now it's 0.7. So this is a very conservative way of getting at a design answer. You may not want to do your entire design this way. You may want to do this as a preliminary design approach. You can always use that table to give you a rough idea of what your B2 is going to be. Because if you can figure out a drift limit and a load ratio, you can go into that table and get it directly. I want to move back to that table for just one thing and point out that there is this black area up at the top. All right, all of this area up here. And the reason that it's black is because B2 would be greater than 1.5. And of course, you can't use the effective length method if B2 is greater than 1.5. All right? So in conclusion, what's really new? You must consider initial out-of-plumbness. And I can't emphasize too much that word consider, because we've seen that in fact we don't have to do anything with it much of the time. We have an opportunity with the direct analysis method to not have to calculate K. We have something new in notional loads, and these notional loads are there to account for things other than the notional load. They're there to reflect something else. And the bottom line is we have 3 methods that we can use. We can use the effective length method that we've been using all along. We can use the direct analysis method, or we can use the first order analysis method. I would encourage you to look this stuff over, study the handouts, make sure you take advantage of all of the opportunities here. There was a time when we might have said, from AISC's perspective, everybody should be using the direct analysis method all the time. But as we've progressed through the 5 years of the 2005 specification and now with the 2010 specification and have a better grasp on how these things actually play out in practice, I encourage you to learn all three methods and learn to apply them in the situations that are best suited for what they are and for what the project is that you're working on. I thank you very much. I appreciate your attention, although I can't tell because I can't see you. I assume that you all have been riveted to your computer screens. And if you do have any questions, feel free to post them and email them to us. We'd be happy to answer any questions. Brent, I'll turn it back to you.
All right. Thank you very much, Dr. Geschwinder. We do have a couple questions, and we've got a few minutes, so I would like to have you address a few of these. There was a question earlier about the M1, M2 applying to the no translation analysis. Back in example 1, the moments that were used for that example were due to lateral translation. However, we discussed earlier that it should be related to no translation. Can you clarify that?
Well, then I made a mistake. Let me go back here in my handout. And
if you go back to slide 33.
33, huh? I don't doubt that I did that, and the questioner is right. If that's what I did, I should not have. Well, 33 isn't the example, though.
Oh, so go back to, I'm sorry, go to slide 69 in the example.
Ooh.
Sorry.
Right. Yeah, well, if those are lateral, yeah, I got caught in that thing again. Now, what's happened here is there is no moment due to the no translation, and therefore there is no need to calculate B1. So I should not have calculated B1 in this particular case. So yes, the use of the no translation moments here is incorrect. And whoever pointed that out, thank you. I appreciate it. It's amazing how many times you can do one of these things and miss some of that kind of stuff.
Okay. Question, are these first and second order effects considered that you know of? Are they considered in commercial software programs?
Yes, but the real key is how does your commercial software do it, okay? Now, I'm guessing that if you have a very old version of something, it may not. But if you have a modern version, as far as I know, all of the modern commercially available software that is used in the building industry has some way of accounting for second order effects. You need to find out what method they use and make sure that you're comfortable with that. It's easy enough to ask your software vendor representatives for their references. They will be happy to tell you what they do and how they do it and give you the technical publications and so on. I know these people. They participate in our committees. We go to presentations together, and they know that I am telling you this because I tell it to people all the time. They are happy to have you contact them. Every one of them thinks their software is better than everybody else. And so if you're questioning it, they're going to want to show you, this is how we do it. We think this is the best way or the right way. So go out and ask it. Get input from them. It's your seal on the drawings, not theirs. And so you need to be comfortable that the way they're doing it has a substantial credibility.
Okay. And then one of our attendees has asked if you have any thoughts on applying the direct analysis method in a bridge design situation concerning either a top chord of a truss or, say, a rib of an arch?
Well, I'm not a bridge guy, and certainly the AISC specification doesn't apply to bridges. But I know that there are engineers who have used this kind of an approach for structures other than buildings. And it comes from a well-understood, understanding well the behavior of structures. Now, I don't think that if it were me, I would just jump right into it and do it without thinking. I think I'd want to do some bounding of the problem. Keep in mind that the whole idea behind the direct analysis method is that by using a reduced stiffness, you can eliminate calculating K. And so that's what you're trying to do. You're trying to eliminate the need to calculate K. So you might do it, a simple problem, do it with whatever your old way was, and do it with the direct analysis method. See how close they come. Try to reconcile what's going on. But I would say, yeah, it should apply.
Okay, and one more question. Do we use the reduced stiffnesses for drift calculations or just for stability consideration?
Just for stability considerations. If you're talking about drift for, I'm going to limit the drift of my building, no, you don't use the reduced stiffness. The only time you use the reduced stiffness is for stability calculations. Okay, if you're talking about deflection of a beam, right? You may have a beam in your structure that's part of your moment frame, and you're worried about the deflection on that beam. You don't use the reduced stiffness for calculating that deflection. And this is one of the problems with if you're writing your own software, for instance, or if you have software that doesn't accommodate this. Someone might suggest, well, why don't you just arbitrarily put in a smaller modulus of elasticity, that and a smaller shear modulus, and that should take care of it. Well, that will, but if you've got a design package associated with that, and then you use that reduced modulus of elasticity in the design side, then all of your width-thickness relationships are off, and those kinds of things no longer are valid. So you have to be careful with how you go about applying it. Keep in mind that all we're talking about is a way that we can get away without having to calculate the effective length factor.
All right. Thank you very much, Lou.